Assalamu alaikum and welcome back again. So in this lecture we are going to discuss the classification of the signals, and based on this classification we can say that we can classify them into the following uh, 5 categories, that is continuous time versus the discrete time signals, even and odd signals, periodic and aperiodic, also called non-periodic signals, and deterministic and random signals, and the final category is energy signals and the power signals. So today we are going to discuss the remaining classes of the signals. In the previous lecture we talked about the first two category or first two classification of the lecture of the signals, that were discrete time versus continuous time, and even versus the odd signals, right? So you understand that based on the value of the independent variable we can classify the signals whether they are discrete or continuous. So specifically we talked about the discrete time because the independent variable was time, so discrete time signal and the continuous time signal. In case of discrete time signals, the independent variable had discrete values, whereas for the case of the continuous time signal, the independent variable had the continuous values, right? Then the second classification, that was based on whether the given signal is even or odd, right? So even and odd signal can be discrete time and they can also be continuous time, right? So we defined the even signal if the signal is symmetric about the vertical axis or time origin. If it is not if it is antisymmetric about the time origin, then such a signals are called the odd signals, right? So there are signals that are even, there are signals that are odd, and there are signals that are neither even nor the odd signal, right? So in this lecture we are going to discuss the whether the given signal is periodic or aperiodic, and the second category will be, in fact the fourth category will be whether the signal is deterministic or random, and the fifth one is whether the signal is energy signal or power signal. So let's start with the classification based on whether the given signal is periodic or aperiodic signal. So in case of periodic signal, continuous time periodic signal, we say if x of t equals to x of t plus the capital T, right? You understand this is this small t, this basically signifies that it is a time domain signal, and because t has continuous values, so it says that the signal is continuous, right? So continuous time domain signal. So if x of t equals to x of t plus the capital T for all values of this t, then we say that this signal is basically a periodic signal where capital T is positive constant, right? So it can be said a periodic signal are unchanged by the shift t. That means if we shift the periodic signal by amount of t, it will be unchanged, it will have same, right? So if this condition is hold, that is x of t equals to x of t plus the capital T, then we say that that means if this is satisfied for t equals to t naught, then it is also satisfied for t equals to 2 t naught, t equals to 3 t naught, t equals to 4 t naught, and so on. Now, for example, we take the simple example of periodic signal, which is the day. So you understand day repeats itself after how much time? That is 24 hours, right? So the value, that is T naught, is equal to 24 for the case of the day, right? So that means day repeats with 24 hours. It also repeats with twice of the 24 hour, which is 48 hour, 3 times of the 48, which is 72 hours, and so on. So that means if something is periodic, if some signal is periodic with period T naught, then it is also periodic with period 2T naught, 3T naught, 4T naught, 5T naught, and so on. So again, then the question comes, the value fundamental, that of the fundamental period. So the smallest value for which this holds is called the fundamental period, right? So for example, in case of daytime, 24 is the smallest value, right? Because day repeats after 24 hours, it also repeats after 48 hours, 72 hours, 96 hours, and so on. So day is periodic with 24, 48, 72, and so on, right? So the smallest value is 24. So this 24 is called the period, is called the fundamental period. So we understand that there's a relationship between the time period and the frequency, that is, they are reciprocal. So in case of linear frequency, for example, we say, because you understand, right, one is linear frequency and one is the angular frequency. So the unit of linear frequency is hertz, and it is represented by small f. So small f equals to 1 over the time period. So we can say, also say that you understand that f has units of hertz, or we can also say f has units of 1 over second, right? So that means because the relationship between the linear frequency and the angular frequency is that 2 pi f basically equals to the angular frequency, 2 pi f. This is equal to the angular frequency, which is denoted by omega, right? So the unit of the discrete linear frequency is hertz. So the unit of the angular frequency is radians per second, right? So because 2 pi w equals to f, that means we can write, so that means we can write f equals to omega over 2 pi, right? So f equals to omega over 2 pi. That means if I replace value here, then that means 2 pi by omega equals to 1 over t. So for the case of fundamental period, and so we can say, or we put 0 here or not here, so we can say, okay, that's the fundamental frequency, right? So that means we can write the, okay, so that's basically f equals to 1 over t, right? So f equals to this one, omega by 2 pi. So that means we can write omega naught, right? That's fundamental frequency, or 2 pi equals to the 1 over period, right? So that means we can say, so that means shifting this 2 pi to this side will shift it from denominator into numerator. So that means we get this relationship. So that's a relationship between the fundamental frequency in radians per second, right, and the fundamental period t naught. So that's the relationship. Okay, so fundamental period corresponds to the fundamental frequency, and when the period is small s, then the frequency will be the largest, right? So you understand the uh, reciprocity, right? That's the frequency and time period, they are reciprocal, so increasing the one will result into decreasing the other and vice versa. So let's take some examples of the periodic signals shown on here, right? So this, if you look at this signal, it is repeating itself, right? So repeating the value, so that means it's a periodic signal, right? The period for the signal is t naught, so every t naught it repeats, right? Similarly, this is again signal of the periodic signal, which examples of the periodic signal which is repeating, right? And that's another waveform. So because they are repeating, so they are periodic signal, right? Now any signal for which there is no value of t to satisfy the condition, that is x of t equals to x of t plus t, is called aperiodic or non-periodic signal. So again, some more examples. So these are sinusoidal signals, right? So that's the on the top one, and this one shown, this is a cosine waveform, and you understand it's a periodic signal, right? And again we have the sine waveform here. This one is a sine waveform, so that's the example of the periodic signal, right? So to show different waveforms, so that you understand that sinusoidal signals are not alone that are the periodic, right? So periodic signals can be sinusoidal signal, they can be sawtooth waveform, they can be square wave, they can be rectangular wave, they can have any waveform. For periodicity, important thing is that it repeats, not important, the must thing is that it repeats. If it is not repeating itself, then such signals are called the aperiodic signal or non-periodic signal, right? So non-periodic signals are shown to the right of the figure. So this is an example of aperiodic signal. You understand it doesn't repeat. In fact, it's just a single pulse, right, that exists from this time to this, and after that it is zero, and before that it was zero. So this is an example of the aperiodic signal. Another signal that is aperiodic is this one, that is the exponentially decaying signal, right? So that's also aperiodic. This one again another signal that is the that is exponentially growing signal. So they are again aperiodic signal, right? Again, if you look at this one, this looks like a something sinusoidal waveform, but you see that after each cycle, right, it is dampening, it is reducing, it is decreasing. So that means the value here, you can see that is 50. Again, after one cycle, that may be a 2 pi, right? This peak is reduced to 30, and again it's reducing. Either you can see that both, whether the positive peaks or the negative peak, they both are reducing. So that means the signal is just decaying. So this is an example of the non-periodic or aperiodic signal, right? And similarly, if you look at this one, you see it's repeating itself. The value here is exactly same, which is here, which is here, right, and so on. So if you look at those peaks, so similarly for the negative peak, the value here is exactly what it is here, is exactly what it is here, and so on. So you see these values are repeated. So when the values are repeated with a certain interval of time, then we call such signal as periodic signals. So these all signals you can see are basically periodic signals and aperiodic signals for the continuous time case. Discrete time signals can also be periodic, right? And they can also be aperiodic, right? So for example, we have discrete time signal x of n. So for a discrete time signal x of n to be periodic, right, it must satisfy this equation, that is x of n plus the capital N should equal to the x of n, and this is for all integer values of n, right? So if this equation or this condition is satisfied, then we call that this signal x of n is periodic. And when, right, so again, like we said for the continuous time case, that capital T should be positive. So again, the condition for a discrete time signal to be periodic, its period, which is capital N, should be not only positive, but it should also be not only it must be positive, it must also be an integer, right? So if n is not integer, in that case the resulting signal will not be called the periodic signal, right? So again, like we said, there is a concept of the fundamental period, that the smallest value where we defined that smallest capital value of smallest value of the capital T where the equation was satisfied, we called it fundamental period. So again, here we also say the same, that the smallest value of n for which this equation holds or is satisfied is called the fundamental period, and corresponding to the fundamental period we have the fundamental frequency. Any discrete time signal for which there's no value of n that satisfies this condition will be called as non-periodic signal, right? Now, because we have two conditions for periodicity in case of the discrete time signal, that is, it must be value of the period must be positive and it must also be integer. So the equation relating the frequency to the period is this one, where it is said that n by m should be equal to 2 pi by the capital omega. You understand, we represent the frequency of the discrete time signal by the capital N, right? So that you may not get confused, because for the case of the continuous time signal, we represent the frequency by the small omega, whereas in case of the discrete time signal, we represent the frequency by the capital omega. Now, for the signal to be periodic, the necessity condition is that n by m should be equal to 2 pi by omega, and this should be equal to the it should be rational. If this results into some irrational value, then such a signal will not be called a periodic signal. Okay, so whether it's a we have another discrete time signal, that is x of n, and you have to check whether this signal is periodic. If this is periodic, then find its value of the period. I should put 3 dots here, right? 1, 2, 3 to show that it's going on in both the direction, right? So because it's repeating, right? So we can say that this is example of discrete time periodic signal, right? So I hope you can find the period of this signal. Okay, so just check, and maybe you can tell me in the live session what is the period of this discrete time signal. Okay, so on the right side shown is a signal that is Aperiodic signal, this signal exists only from -1 up to 1. It has some non-zero values, whereas for the remaining, that is beyond 1 up to positive infinity and beyond -1 up to negative infinity, this signal has zero values, right? So it's not repeating, so that means it's not repeating its values, right, after a certain interval of time. So we can call such a signal as the aperiodic signal. Okay, so up to now you understand what is periodic and what is aperiodic signal. And so what if you have a signal that consists of summation of the two periodic signals, whether the resulting signal will be periodic, right? So that's an important thing, that we have a signal. So in that case, we say the resulting signal will be periodic. For example, here it is shown that we have a signal x of t, which is composed of two signal x1 of t plus x2 of t, which is composed of their summation, right? And we are given the information that x1 and x2 are basically periodic signals. So we have to check whether x of t will be periodic, right? Now, to know whether x of t will be periodic or aperiodic, the condition is that if the ratios of the periods of the x1 and x2, right? So for example, the period of x1 of t is t1 and period of x2 of t is t2. Then if I take the ratio of the two, right, and if this ratio results into a rational number, then we say this signal is basically, this signal means the resulting signal, that is x of t, will be periodic. If it results into irrational number, in that case we say the resulting signal x of t will not be periodic, right? So then question comes, if the resulting signal is periodic, then what will be the period of the signal? I mean, for example, we take the ratio of t1 and t2, and we just know we find that this is rational. Okay, so that means x of t is periodic. When x of t is periodic, what will be the period, or how we can find the period of the x of t? So that's very simple, that if we write the ratios of the two periods in the co-prime form means that there is no common factor other than 1, right? So then we say this is L over K. So the period of the x of t will be L multiplied by period of t2, or K multiplied by t1, right? And you understand t2 is time period of the x of 2t, and t1 is the time period of the x1 of t, right? So t1 is period of x1 of t, and t2 is the period of the x2 of t. So we can find either find the period by multiplying L with t2 or multiplying K with t1, or we can also take the LCM of the periods of t1 and t2, so we can find the time period of the xt, right? So for example, here we are given a signal x of t, which is equal to cos of t plus sine square root of 2t, right? So we say the cos of t is basically x1 of t, and we say sine of square root of 2t is x2 of t, right? Now to find the period of x1 of t, which is cos of t, because in the standard format, cos of omega t, this is how we write, right? So that means cos of t, if I correlate them, that means omega 1 basically equals to 1. So when omega is 1, we know that the relationship between period, time period, and the angular frequency is that the product of the period with angular frequency equals to 2 pi, or because we know frequency, so we can say period equals to 2 pi by omega, which is given here, right? Now because the frequency omega here is 1, that means by putting 1 we get t1 equals to 2 pi, right? So this is the value of the time period of the cos of t. So right now again we are going we just do the similar procedure for finding the time period of the second part x2 of t, which is sine square root of 2t, right? Now sine omega 2t, right? So in this case, if you look at this one, so square root of 2 is basically the frequency omega 2, or the frequency of the second signal. So because t2 equals to 2 pi by omega 2, so that means we can say that 2 pi by square root of 2, because square root of 2 is a frequency of the second signal. So that means it will result into on simplification we get the time period equals to square root of 2 pi square root of 2 times the pi. Okay, then we check this condition, because if this condition is met, then we say the resulting signal will be periodic, right? So if you write this in the ratio form, that t1 over t2, so if I write this one, because t1 is 2 pi by 2 pi and t2 is square root of 2 pi, so that means it will result into an irrational number. So if this thing results into irrational number, that means the resulting signal will not be periodic. Okay, so this is how we we check whether the resulting signal is periodic, and if you get that the value of the ratios of the two periods is rational, right? So in that case it will be periodic, and you can find the period using this. Okay, you will be given some examples later on after the completion of I think this lecture and the following two, right? So we'll do some you'll be given some homework related to these topics, so that you do it by yourself and we discuss it hopefully in the subsequent lecture. So similarly, because you know that signals can be discrete signals can also be periodic. So for the case of the discrete time signal, there's no condition that their period should be ratio of their period should be rational. You know why? Because they are already integers, so they are right, because the must condition for the discrete time signal to be periodic is that it must be positive, and it also must be integer value. So when you take the ratio of the integer value, it will result definitely into a rational number. So no need to check the condition whether the resulting signal will be periodic or not. It's straight away periodic, right? So if discrete time signal consists of signals or summation of the two signals that are periodic, so that means the signal will be periodic, and you can, using the similar arguments, you can find the period of the resulting signal. Then the fourth category of the classification of the signals is whether the signal is deterministic or it is random. So we will not take a lot of time on this classification. So here we define a signal to be random if there is uncertainty before it occurs, right? So example include the electrical noise generated in amplifier, right? So the amplitude of the noise fluctuates between positive and negative values in completely random fashion. Random signals or waveforms cannot be modeled by explicit mathematical expression, you understand, and we use the probability theory, right? So opposite to the random signal are the deterministic signals, right? So for the deterministic signals, we say that they are explicitly modeled by some mathematical expression. For example, we say x of t equals to 5 cos of 10 t, right? So by putting any value of the t here, you understand, right? By putting any value of t here, we get the exact value, right? So that means they are deterministic. We can determine their value by just putting the value here. But as far as the random signal is concerned, we have no information. Rather, we use probability and we say that it is probable to have this value, right? And this so deterministic signals are those that we don't have any uncertainty with respect to their value at any given time. Okay, so I think that's all for this classification. We will not discuss it in more detail. I hope you you are studying, or maybe you have studied some courses on the probability and those kind of things. So the final classification of the signal, the final category, that is signals, energy signals and the power signals, right? So we know that signals if you talk about the electrical engineering, so we have two types of signal, that is voltage or current, right? Voltage and current. So we have this signal. Now, if you have a system, right, where in fact, if you have a electric circuit, so in that circuit, we have a resistor, right? So that will have the voltage develop across the resistor will be, for example, Vt, and because there will be some current flowing through the resistor, so we say that is It is the amount of current that is flowing through it. Then by basic circuit theory, you understand that the power dissipated in this resistor can be defined as P of t. You understand, T emphasizes that's also a time varying thing, right? So Pt equals to V square, that is square of the voltage divided by the resistor, resistance of the resistor, right? So in terms of, if I write the current, then I say the total power dissipated, not total, in fact instantaneous power dissipated in the resistor is also equal to I square T by R. Again, T signifies that I is basically time varying. I, you understand, is current, and that is time varying quantity. So in both the cases, the instantaneous power Pt is proportional to the square of the amplitude of the signal, right? Because in once we write in terms of voltage, so we say V square R, V square by R, and in other equation, the instantaneous power is written in terms of the current, that is I square T. So if I take, if we consider that the resistance involved, the resistor involved has a unit resistance, right? So it can be, for example, 1 ohm, or it can be 1 kilo ohm, or whatever. So we say it's a unit, right? So if we say unit, then it means that in both equations we can say that power, the instantaneous power dissipated equals to V square T, and in the second one, the instantaneous power dissipated is basically I square T. So that means in both cases, because this is the voltage, that's also a signal, and that's the current, that's also signal. So if I just generalize it to just write it x of t, because square, whether it's a voltage or current, because square of this will result into the instantaneous power dissipation. So we can say that P of t equals to x square t. So that's the instantaneous power, right, dissipated. Now, so the total energy of the continuous signal x of t can be written as, you understand that power relationship between the power and the uh, energy, right? So the instantaneous power is this, so the total energy will be obtained if we take the uh, integration if this is for the continuous time case and summation for the discrete times, right? And for all time values, that means limit t tends to infinity minus t by 2 to t by 2 integration, right? That's so, and this will result into the total energy. Now, for aperiodic signal, the period will be infinity, right? So we can say that in that case, energy is minus integration of x of t square from minus infinity up to infinity, right? Now, and the relationship between the energy and power, you understand, if I scale it by 1 by t, so it will, right? So this will result into the power, right? So I can say that um, limit t tends to infinity 1 over t, and this is minus t by 2 up to t by 2. So I get this power, right? So that's the average power, time average power. So that's the expression for that. So hence the time average power of periodic signal, because you understand periodic signal has some fundamental period t. So instead of saying limit t tends to infinity, because now it has some finite value of a period, so we can say that this is, so this is the expression, right? So this is the expression for finding the uh, power, right, in case the signal is periodic, because if it is aperiodic, then t will be infinity, right? T means time period, right? And this is expression for finding the energy, right? So because for it, this one, right, you can use either that or they're same. There's some problem. Okay, so this is the equation for, there's some problem with okay, so this is the expression for finding the energy of the continuous time signal, right? And this one is the expression for finding the power if the signal is periodic, right? So if the signal is periodic, we take the square of the signal and integrate it over one period, right? So that's minus t by 2 up to t by 2. You can also take from 0 up to t or whatever, but the length considered should be one period, right? So that's how you find the power for a periodic signal over one period. And this is the equation, either top one or this one, because in this case we say time tends to infinity, that is time period tends to infinity. So in that case we say it's square and sum over one period, right? So that gives you the energy for the continuous time case. So for the case of discrete time signal, similar to what we had there, we had integration minus infinity up to infinity x of t absolute square, right? So because you understand the difference between continuous and discrete values, there is some problem with the software. It's just okay. So right, so this is how you find the energy for a discrete time case, because in discrete time case n is you understand that is integer. So when n is integer, we can use the summation, whereas the continuous counterpart of this equation is that if you recall, that is e equals to, right, integration and there we take the limit from minus infinity up to infinity, and we say xt absolute, right, and square of this, and then d of t, right? So it always reminds you that d of t means you are dealing with the time domain signal, right? So this is the equation, right? So this is how you find the energy for the case of continuous time signal. If you compare the two, you can tell that they're same, because not same, similar, because here continuous values, so we take integration, here discrete values, so we take the summation, and here we take integration from minus infinity up to infinity, and again here we take summation from minus infinity up to infinity, right? So same type thing, because discrete, so summation, continuous, integration, right? Discrete, you take the difference, continuous, you take the differentiation, right? So again, for the expression of the power, we wrote similar expression, right? So here we say limit n tends to infinity, there it was limit n tends to capital T tends to infinity, and again it's 1 by 2 n plus 1, so again there we scale 8 by, so because we are summing it from minus n to n, that's why we are taking 2n plus 1. There we were summing it, integrating it from minus t by 2, that means here you're taking two interval of the two time periods, right? So that's why you are dividing it by 2. You can also take a single and you can say, okay, and run from minus n by 2 up to n by 2, and then you take the single n here. So I hope you can grasp the concept. So similar to what we had for the continuous time case periodic signal, in case of periodic signal we find the expression was something like, you say p equals to, right, p equals to 1 over t, right? And if I just write t here, I hope you understand. T means that you are integrating it over one period, right? So that's then we said x of t, that is your constant signal, absolute of that, and then you square, and then you integrate, right? So that's the equation for the finding the power, right, for a continuous time case, right? So in case of continuous time signal, you have this thing, right? And in case of discrete time signal, so you have this expression. I hope this is quite similar, so you can appreciate and you understand how, right? So you can correlate them. So I think it's easy, right? Then we say what is a power signal or what is an energy signal, right? So by definition, any signal is said to be energy signal if it has energy which is greater than 0 and less than infinity. In other words, we can say a signal is said to be an energy signal if it has non-zero finite energy. If the energy of a signal is 0, right, or if the energy of a signal is infinity, this signal cannot be called an energy signal, because it is must for a signal to be called energy signal only if it has a non-zero finite energy, right? So that means if 0, you cannot call it energy signal. If energy is infinite, you cannot call it energy signal. Similar definition is for the power signal, that the power a signal can only be called a power signal if its power is greater than 0 and it is less than infinity. In other words, we can say that a signal can only be called a power signal if its power is non-zero finite, right? So if the power is non-zero and finite, then we can call this signal as power signal. Otherwise, it cannot be called a power signal. And you understand what is otherwise. Otherwise means if you get a power equal to infinity, or if you get a power equal, right, if you get a power of a signal equal to 0, so you cannot call it a um, power signal. Okay, so for example, we have a signal equals to x of n. The first question, and we have to find whether what is the power of this signal. Okay, find the energy and power of the signal. For example, what is E of this signal and what is P of this signal. Right, so I hope all of you understand this is x of n. So x of n signifies that it is a discrete time signal. Right, now n can have value from minus infinity to up to infinity. So what does it mean? Is it a power, is it a periodic signal or aperiodic signal? So right, so I think you can plot and you know that at 0, because it's a constant signal, right, irrespective of the value of n, it's always 4. So that means if I plot this signal, so at 0 it has 4 value, at 1 it has 4 value, at 2 its value is equal to 4, right? Okay, so I just plot the 3 here. Okay, one more here and one more here, and they all have amplitude equal to 4, not 1 by 4. Okay, 4, right? So this is your minus 2, this is minus 1, this is 0, this is 1, right, and this is 2, this is your n, and it's extending in both the direction, right, positive and negative direction. So do you think it's a periodic or it's an aperiodic signal, right? So a signal is said to be periodic if x of n plus capital N equals to x of n. So if you put this, so you realize that this is basically a periodic signal with period equals to 1. Okay, so it's a periodic signal. So let's see what is the energy of this signal, right? So E equals to summation n running from minus infinity up to infinity, right, x of n square, right? So by putting value, you understand that if you sum it from uh, minus infinity, right, and running from minus infinity up to infinity, right? So what is the value of this signal? That is 4. So 4 square means, right, so it will be something like 4 square, so which is equal to 16, right? So that means if you sum this, right, so that means dot dot plus 16 plus 16, right, 16, if you sum it, right, if you go all the way from minus infinity to up to infinity, and this is 16, so if you sum it, so I hope you understand, you will get infinity, right? So this signal has infinite energy. So you understand, if something has infinite energy, we cannot call it an energy signal, because for a signal to be energy signal, its energy must be non-zero finite energy. That means its energy should be greater than 0 and it should be finite. So in this case it results into, you understand, right, this square of 4 is 16, and you sum it from minus infinity up to infinity, so it will come into it will result into infinity. So okay, let's see again what is the equation for finding the period, right, sorry, power. So equation for finding the power is P equals to, right, 1 by n summation, right? So we just consider the single period, so that is so this is equal to n equals to 0 up to n minus 1. Okay, so that means you are just summing it over one period, so it's up to you. You take 0 to n minus 1, that's also one period, or you can take minus n running from minus n by 2 up to this. So in short, you take the summation over one period, right? So that is x of n, and you take the absolute square. Okay, so that's the thing. Now you understand n equals to 1, so it will be 1 by 1. Then you say, okay, summation n running from 0, so that means n equals to 0, and the upper limit is n minus 1, right? So n equals to 0 up to, very eager, I think just 0, because 1 minus 1 is 0. So you have x of n square, x of n square. What is the value of x of n? That's 4, so the square of this will result into 16. So you get 16, right? So now you see that you get power equals to 16, okay, and energy for this particular signal is infinity, right? So what do you think? Is it a power signal, or is it a power signal, or it's a energy signal, right? Oh, it's again teasing. Anyway, so these are the values you get. For power you get 16, and for energy you get infinity. So because a signal cannot be called an energy signal if it has a 0 or infinite energy, so this is not an example of energy signal. Again, for the power, yes, we say a signal is said to be a power signal if it has non-zero finite powers. So 16 is non-zero and also finite, so that means it is a power signal. So I think with that we end the lecture for today, and we'll meet in the next lecture. So that's all for the classifications of the signal. Okay, so go through them, and if you have any question, I think I would appreciate you ask the questions, because when you ask the question you learn a lot, right? So see you in the live session. Until then, Allah Hafiz.